So over the last two lectures, we have been exploring the working of fiber lasers, regarded as an industrial work. And today too, we continue our journey with this fiber laser. We know that if we take an appropriately cladded fiber and launch a ray of light on the core clad interface in such a way that the angle of incidence exceeds the critical angle, then this ray of light travels down the fiber core in such zigzag path, always experiencing total internal reflection every time it is incident on the core clad interface at an angle exceeding always the critical angle. And thus, guided by this judiciously cladded structure, this input beam, as we just saw, travels down the fiber core. And as it travels, it energetically excites the light emitting species doped in the pure glassy core of the fiber, just like what happens in a solid state laser that we have studied in great detail quite a number of weeks before when we studied solid state laser. In solid state laser, however, the gain medium is actually in the form of a cylindrical rod called the host, into which the light emitting species are doped. In this fiber laser too, the host is in the form of a glass strand of, if its diameter were a couple of centimeters, say 2 centimeters, and length is say 20 centimeters, quite typical of the operation of conventional solid state lasers. This diameter would be few micrometers to say millimeter, and length could be meters to even several kilometers. So that is the difference. But nevertheless, the light emitting species are embedded in this. So as the pump beam travels through this glassy core, the active atoms, that is the light emitting atoms, will absorb this light. Very qualitatively, the lasing that is based on a 4 energy level configuration can be described qualitatively this way. This is the ground state, where in the beginning all the atoms are residing. This is the upper laser level, and this is the lower laser. The upper laser level is usually metastable in nature, so that the atoms or molecules, when they arrive here, they stay here for a long time, so the population accumulate here. Now, so if I draw it in a bigger scale, so this is a fiber, this pump beam has been launched, so it is traveling down the core by this zigzag paths, undergoing total reflection, total internal reflection. Every time it interacts with the, this is the clad This is the core. So every time it interacts with the core clad interface. Now we have our light emitting species docked into this glassy core. So this is the pump beam, appropriately chosen, of course. So its wavelength, we call it lambda p. So the photon of this wavelength, as it interacts with this species, as it travels down this fiber, will excite them to the pump level. This is the pump level. And then it very quickly relaxes. I'm not going into detail. The principal operation is like any other solid state level. Relaxes down to the upper level. And as it comes down here, it will of course emit spontaneous photon and drops down to the lower level. And these photons, suppose let us just take this atom, which has absorbed this light and has been excited. And if it has been excited, it will emit light spontaneously in all possible directions. And this light will have a wavelength which is more than this, because this energy is more than this. So the wavelength of light that will come out of this transition will be longer than this. So I actually should have used this as say blue and this as red to indicate that its wavelength is more. Okay, it doesn't matter. I just would use this to distinguish these two lights. I will just use it in another color, say this color. So the light, spontaneous light, can be emitted from here in any direction. All these excited species which are lying in the upper level spontaneously emit light, and this light can travel in all possible directions. Now the light that will shine onto this interface at an angle again exceeding the critical angle. Now note one important point. The critical angle in the previous case for this wavelength, say we call it theta c1, and critical angle now in this case, because the wavelength has changed, the wavelength, let us say that this wavelength is lambda L, so this is lambda L. So for lambda L, the wavelength has changed, so the refractive index of both the core and clad also will be different, and therefore the critical angle, which is a function of the refractive index of core and clad, would also be different. So now the critical angle, let us say this is theta c2. So now if this angle of incidence exceeds theta c2, then this will again undergo total internal reflection as it would travel down this core. But this is the spontaneous light emitted from this transition. So what has happened? This pump beam is traveling through the fiber, and in the process it has excited some of the species which will perform as the light emitting species, and then they will, after they drop down to the upper level, they will emit spontaneous photon, which if is incident at the right angle, that is at an angle exceeding the critical angle on the core clad interface, would again travel down the fiber core without any spillage of energy through refraction. So then, summarizing then, a fraction of the photons spontaneously emitted by these excited dopant species. They have been excited by the pump photon that strike the core-clad interface at angles exceeding theta c. So we call this as theta c2. Will be trapped and guided in the core once again by total internal reflection, just as the palm beam was also being guided through total internal reflection. These spontaneous photons understandably perform the role of the seed photons for stimulated emission and can result in the amplification of light with appropriate cavity feedback. I hope I have understood, you have understood the underlying physics of the operation of a fiber laser. That is, you have pumped, and the pump light you enter in a way that it is guided into the core of the fiber, and as it traverses down the core, it excites the light emitting species, and then they would spontaneously emit photons. A fraction of that would again shine onto the core-clad interface at an angle exceeding the critical angle for that wavelength. Then they will perform the role of seed photons for triggering stimulated emission and would result in amplification of light the normal way it happens for any other laser, with appropriate, of course, with appropriate cavity feedback. However, before gaining deeper insight into the working of a typical fiber laser, we need to familiarize ourselves with the concept of the acceptance cycle. Let us see what is the acceptance cycle. Let us consider, so this is pumping in the form of a conical beam. This is the conical beam that is shown in 2 dimensions. This drawing is of course in 2 dimensions. Basically in 3 dimensions, this beam is a cone, and it strikes incident on one end of this fiber in the manner as shown here. Let us pick up a ray A, which we call ray A, which marks the lower boundary of the incident light beam. This is the lower boundary of the incident light beam, and this ray is the upper boundary of the incident light beam. Now, this beam strikes this interface. This interface actually between this is usually it will be an air, and this is the fiber. So this is basically this is core, that is the glass. If it is a glass core, so this is glass. So this beam actually strikes this interface, air glass interface. Now we pick up this ray A, and as it strikes this, it will undergo a refraction because it is incident from air to the air glass interface. So as it enters the glass, it will undergo refraction at this point. So this is the normal to this. So if we extend it, this is the normal. And for this ray, this is the angle of incidence. So the ray bends towards the normal. So this is the angle of refraction. So after its refraction into the core, it strikes the interface of the core and cladding. So it strikes the interface of, this is the core and this is clad. It strikes this interface at an angle which is critical for this wavelength. For this wavelength of light. So let us say this, we call it lambda palm. For this wavelength, this is the critical angle. So it strikes this ray which marks the lower boundary of this beam after its refraction at this interface strikes the core clad interface at an angle which is exactly critical angle. So the refracted ray would graze over this surface, core clad surface. Although not shown here, but we can easily show that this ray that defines the upper boundary of this beam, that is this ray, will also again undergo refraction here, and it can be shown that this ray too will fall on the other at an angle which is again theta c, that is the critical angle, and therefore would graze over it once again at the graze over the core clad surface. The end result is, and it can be shown that any other beam lying between these two end rays, one defining the lower end, the other the upper end, would, after refraction on this air glass interface, would strike this core clad interface at angle that will lie between theta c and 90 degrees. That means all these rays will undergo total internal reflection because the angle of incidence for all of them will exceed the critical. Thus the end result is the confinement of this entire incident conical beam represented here in 2 dimensions inside the fiber core. The angle of this conical beam is actually the acceptance angle, because all the rays lying inside will be guided through this core without any spillage of energy through refraction. This angle mathematically can be expressed as this: theta acceptance angle equal to sine inverse 1 by mu 0. Mu 0 is the refractive index of the surrounding medium, which essentially is air, therefore can be taken as 1. This can be taken as 1. Square root mu core square minus mu clad square. In order to drive this point home, the trajectory of another ray, which is B, trajectory of another ray, which is B, this ray is shown here. So this ray is incident at an angle which is this, and therefore it will be reflected at an angle which is more than that of ray A, and therefore strike, it can be easily shown the core clad interface at an angle which is less than critical angle, smaller than critical angle, consequently does not undergo total internal reflection, and a part of its energy spilled out through refraction. A part of this energy spilled out of the core as a result of refraction. So I hope you have got a fairly good idea onto what is an acceptance circuit. Let us now delve into the pumping of a fiber and its lasing. Like any other solid state laser, as we now know, fiber lasers are also optically pumped. Any solid state laser we know about by now that has to be essentially optically pumped, except of course semiconductor laser, which we will study just after we end our study with fiber laser. Although the very first fiber laser that we know was operated in 1961 did make use of side pumping, their long strand-like shape makes this laser unsuitable for pumping through the side because the huge surface area that it presents is very inefficient for pumping through its side. It's very challenging. It can be pumping very feebly. And therefore, the huge surface area, which should essentially allow efficient dissipation of heat that will be deposited inside this core, stays unutilized. This potential stays unexploited if the pumping itself would be so weak. I would like to mention here an interesting fact. See, when I think the first fiber laser was developed by Snyder in 1961. So the first fiber laser that Snyder developed in 1961, he used a flash lamp and wound the fiber, glass fiber, around it like a spiral. And the light emitted by this flash lamp, a small part of the light could actually pump the dopant substance that was seated inside this glass. And this was operated in 1961. In contrast, the very first laser that Mayman operated in 1960, if you remember, this is the flash lamp, and Mayman used his rod, solid ruby rod, and pumped it by a helical flash lamp. The flash lamp was wound around it in the form of a helix, and the rod, ruby rod, was placed at the center of the helix. And in this case, the optical fiber took the shape of this helix, and the flash lamp, this is the flash lamp, was wound around it in the form of a helix. Just for sake of mentioning, it is of interest to note here. Furthermore, the difficulty of coupling the divergent light emitted by a conventional source through the tiny end of the fiber. As I said, the fiber diameter can vary from few micron to a millimeter, sub-millimeter. It is so tiny that it will be difficult to couple the divergent light emitted by a conventional source through the tiny end of the fiber. It was primarily responsible for putting any serious research on fiber lasers on hold during the 1960s, 1970s, and also major part of 1980s. The advent of heterojunction diode laser, which is of course also called semiconductor laser, in the 1980s, offered the prospect of transporting light efficiently through this tiny end of the fiber, and led to the resurgence of interest in the research on fiber. We will explain it, elaborate it in more detail very soon. There has been no stoppage thereafter, and these lasers have now exploded out of the laboratory into the numerous applications profoundly impacting humankind. Now, for end pumping to be effective, the light must enter the core of the fiber within its acceptance angle. See, this is the fiber, and this is the clad. This is the clad. This is core. This is clad. And so the acceptance angle, suppose this. So the beam must be lying within this acceptance angle so that it is very well guided into the core, and the core actually would be docked with this light emitting species and therefore would be efficiently excited by this light, pump light. Now these sources are usually much too large and emit into an angle that is too wide to allow any meaningful coupling of the light into the fiber core, because if the core source itself emits light widely diverging angle, then meaningful coupling would be very difficult. The diode lasers, on the other hand, emit from a tiny area into a much narrower angle that can be effectively transported into the fiber core through its end. The diode lasers also is very tiny, the semiconductor lasers, and it really fits well as far as end pumping of the fiber would be concerned. Fiber is concerned. As we have seen, pumping by its side would be very, very challenging. So it has to be pumped through its end. But this very tiny area makes it very difficult to pump. But diode laser fits the bill because it also emits a very narrow beam of light. So once inside, the pump light, once it goes inside, as we know, we will be now guided through the length of the core by the phenomena of total internal reflection. For a diode laser of appropriate wavelength, the light will be gradually absorbed by the doped species as it travels down the fiber. I think I would end here today, and in the next class we begin right from here, and we'll see as to how this pump beam, as it emitted from a semiconductor laser, as it traverses down the core of the fiber, how it eventually results in the generation of the fiber laser output.